Okay, moving forward with this dartboard analogy. If we had a single dart, then the relative areas of each section of the dartboard represents the probability that that section gets occupied by the dart. On the other hand, if we have a whole lot of darts, then the relative areas represent the proportion of darts in each section. We might also have boson darts, where as many darts can occupy each section as you want, or you could have Fermi darts, where only one dart can be in each section, and the whole system shown to the right has a maximum of 1, 2, 3, 4, 5, 6 darts. To understand the partition function, we conceptually replace the dartboard with a list of energy storage modes: rotation, translation, bending, symmetric stretch, and asymmetric stretch. We replace the darts with little quanta of action. A quantum action is thrown at the dartboard. So a quantum action dart is thrown at the dartboard of energy storage modes, and it has a certain probability of being stored in each mode. So the energy stored by the dartboard when this quantum of action is thrown at it depends on what mode that you're in. The translational kinetic energy, I call it linear up here. Linear kinetic energy is going to be 1/2 mv squared, or p squared over 2m. So I'm sending this quantum of action toward a carbon dioxide molecule, for instance, and when I send that, it's either going to cause the thing to accelerate linearly, to begin to rotate, or to begin to vibrate. So next question I'm going to ask is, how big is this action quanta? How big is that dart? How much energy is it going to store inside the system? What I'm going to say next feels like such an unfamiliar statement that I almost think I made it up. Angular momentum is quantized by steps of Planck's constant. It seems to me that if this is true, then it should be at the forefront of any education in quantum mechanics. I think it is common knowledge that within quantum mechanics, energies are quantized, or time is quantized, or space is quantized. Well, whatever. Something is quantized. Something is quantized, and soon after that is said, someone really smart will throw up their hands and say, nobody really understands quantum mechanics. But really, before we join the fatalism, really the first question of any quantum mechanics class should really be, what is quantized? And the answer to that question is action. Action is quantized. Okay, so all of these things have units of kilogram meters squared per second. Angular momentum is the moment of inertia times the radial velocity. The moment of inertia is kilogram meters squared, and the angular velocity is radians per second. A radian is a meter per meter, so this is kilogram meter squared per second. P times x is momentum times distance. Kilogram meters per second is momentum times meters, would be kilogram meters squared per second. Energy times time is a joule second, which is kilogram meters squared per second squared, times the second. You cancel out one of the seconds and you get kilogram meters squared per second. What is the quantum unit of action? I'm not entirely sure, but I think it is either h bar, or h bar over 2, because I've seen these come up in various equations on quantum mechanics. Planck's constant is 662.6 atto joule seconds. I say atto because there's no prefix for 10 to the negative 36, but there is one for 10 to the negative 18th. So use it twice and it comes to 662 times 10 to the negative 18 plus negative 18. Usually actually written 6.626 times 10 to the negative 34th. But if we accept this given that there is a minimum quanta of action, 662.6 atto joule seconds, can we figure out a minimum quanta of energy for each of the relevant modes, rotational, linear, and vibrational? I'll start by thinking about the angular momentum of the carbon dioxide molecule. Carbon dioxide consists of two oxygen atoms situated 116.3 picometers from a carbon atom. The mass of each oxygen atom is 16 atomic mass units, which are in turn 1.66 times 10 to the negative 27th kilograms. So you can calculate the moment of inertia of the carbon dioxide by adding up the contribution of both oxygen atoms. There's two oxygen atoms times the mass of each oxygen atom times the distance to each oxygen atom from the center. So it's 2 times 16 times 1.66 times 10 to the negative 27th times the square of the distance, 116.3 picometers. So I ran this through Mathematica, defining the AMU being 1.66 times 10 to the negative 27th kilograms, the mass of the oxygen atom being 15.994 AMU, and the radius being 116.3 times 10 to the negative 12th, and plugged in 2mr squared to find that the moment of inertia was 7.18691 times 10 to the negative 46 kilogram meters squared. So a couple of kinematic equations relating to linear and rotational kinetic energy may come in handy. This formula for linear kinetic energy is probably familiar, 1/2 mv squared, but perhaps they get less and less familiar as we go down. Linear kinetic energy is also the momentum, the square of the momentum divided by 2 times the mass. And rotational kinetic energy is 1/2 I omega squared, where I is the moment of inertia and omega is the angular velocity. And rotational kinetic energy is the angular momentum squared divided by 2 times the moment of inertia. So L has a minimum value of Planck's constant. So if we plug h into this equation, we already have I, so by plugging h into there, we can find the quantum energy of the rotational mode. So I've done that here, taken h, I've defined h as 2 pi times Planck constant reduced. That's 2 pi times h bar. Anyway, h is h divided by 2 times the moment of inertia, h squared over 2 times the moment of inertia comes out to be 3.054 times 10 to the negative 22nd kilogram meters squared per second squared. Might notice a couple other things I have defined here. The thermal energy is Boltzmann's constant times the temperature. I defined the temperature here to be 300 Kelvin, which is close to room temperature, and figured out that the thermal energy is 4.14 times 10 to the negative 21st kilogram meters squared per second squared. The thermal energy here is kind of telling you approximately how much energy is being exchanged in collisions. It's a measure of the transverse kinetic energy of the individual particles. I should say it is a measure of the average transverse kinetic energy, and by average I should specify it's the mean, because there are several different kinds of average. It's not the median, it's not the mode, it's not the mid-range, it's the mean. The thermal energy here is about 10 times as big as the minimum rotational energy of the atom. So at room temperature, the molecules are bashing around with a huge 4,142 times 10 to the negative 24th, 4,142 yoctojoules of energy, but it only takes about 305 yoctojoules of energy to cause the carbon dioxide to rotate.